This should be a quick one. This is our second part of 10.2, difference of means. Now we're going to be doing a significance test. Same rules apply as before. We should be talking about two different population means, that they're coming from two different places. Okay, then the next thing is, what are our HOs? So again, we write them two different ways. The first way is to compare the first one to the second one. And then the second one is to bring them both over to the left-hand side, right? And then the alternative works the same way. It's either going to be greater than, not equal to, or less than. Same deal here, greater than, not equal to, or less than for our alternatives. All right, so all that works the same way. We're going to be doing the graphing calculator again to have us formulate the degrees of freedom. And then remember that more likely than not, we are doing a T instead of a Z, which means that we will have standard error instead of the word for standard deviation. Standard deviation is the one that has the sigma in it. Okay. All right, so let's go do our last problem on two means and their differences. So in this one, it says, after buying many helium balloons to see them deflate within a couple of days, Aaron and Max decided to test whether helium-filled balloons deflate more quickly than air-filled balloons. To find out, they bought 60 balloons and randomly divided them into two piles of 30, filling the balloons in the first pile with helium and the balloons in the second pile with air. Then they measured the circumference of each balloon immediately after it was filled and then again 3 days later. The average decrease in the circumference of the helium-filled balloons was 26.5 centimeters with a standard deviation of 1.92, and the average decrease of air-filled balloons was only 2.1 centimeters with a standard deviation of about 2.79. So it definitely looks like when they're deflating, if they started out, these are just regular balloons, they're not Mylar balloons, they're just the regular ones, that if they're filled with helium, they are going to deflate a lot faster, right? So do these data provide convincing evidence that helium-filled balloons deflate more quickly than air-filled balloons? Okay, so we need to take a look at this and say, do we truly have two different populations? We do. We actually have an experiment going on, right? We started out with 60 balloons. The first treatment group was 30 of the balloons. The other treatment group was the other 30 of the balloons. The first treatment group was filled with helium. The second treatment group was filled with air, right? Two completely separate populations. So we're okay there, all right? So next is, does it provide? So we're gonna be doing phantoms. So our very first thing again is we have to deal with the parameter. So in our parameter, we're going to be talking about, let's talk about mu sub 1 minus mu sub 2, which is going to be, instead of 1 and 2, let's call them helium and air. Let's use H and A. That's going to be a little bit awkward, but we'll live. All right, so I'm going to call this one H and this one A. Okay, so it is the true mean difference. Let me write this up and we'll come right back. Pathetic scribble, but here we go. So we've got mu H minus mu A, which is the true mean difference in helium called H, and air in balloon circumference. Okay, we could say after however many days, we could seal it from the data providing convincing evidence. So our next step then is our hypothesis test. So for our hypothesis test, we have our null hypothesis and our alternative hypothesis. And in our null hypothesis, we are looking at, is the difference 0, right? So I'd be saying, is H equal to A? And then the other one would be, are they just different, right? Deflate more quickly. We'll have to talk about which way that is. So which one deflated more quickly? It would be the helium one, right? So if I want to show that it deflated more quickly, I would be doing a greater than. Cool? Greater than. Okay, so now I want to move them over. So I'm going to do H minus A is equal to 0, and then I'm going to do H minus A is greater than 0. Okay, next one we go on to is our assumptions. Same three assumptions. We don't have random selection, but we have random assignment. Each treatment randomly assigned to both treatment groups. And then we don't have to worry about 10% rule because we are not doing any sampling, so it's not needed. And then for normal, we just barely passed because we had 30 in each treatment group, so we're okay there. All right, so next thing we're going to do is we're going to go on to what are we doing? What is the name? So our name is a two-sample difference of means. It's going to be a t-test, and it's going to be at an alpha level of 0.05. So now our next step is to go ahead and write how we find a t-score. So that is coming up next. So next one is we're going to do t, and this one I'm going to put on my calculator. Let me get it entered in, and I'll come. So here we go. So we're doing x bar minus whatever the null hypothesis was, and then underneath I've got my standard deviation squared over 30 added together. On my calculator, I'm going to go and run a two-sample t-test. That's going to be in the upper half, and you're looking for it to not say proportion. It should say two-sample. And again, we're going to always assume these are t's. So I don't want it to go and look in my list from my chocolate chip cookie problem from before, so I switched it over to say I just want to give you the stats, and then I just filled them in based on the beginning part of the problem: 26.5, 1.92, 30, 2.1, 2.79, another 30. Picked out the right alternative, which is the greater than, and again, only proportions are pooled, so this is a no, and then we calculate. So as I'm calculating this, you can see that I am getting a t-score of 39.46. Okay, my probability number there is essentially 0. Look at that ending, it's got a -40, so it's essentially 0. And we have a degree of freedom that is equal to 551.43436. So again, I want to draw this. I want to use a t tables or a t-score, so this is t is 0. We're all the way over here at 39.46, and this is a t distribution with degree of freedom equal to 51.436. Okay, so next thing is we need our probability statement. So obtain a probability statement. So the probability that t is greater than, again, I'm looking back at the alternative hypothesis, if t is greater than 39.46 is going to be the same thing as doing t CDF from 39.46 to infinity. And then we would also have to tell it that it is a degree of freedom of 51.436. Okay, and that's going to give us our p-value, but we already know what that is. It's already on our screen. It is essentially 0. So I'm just going to write essentially 0. Okay, that's just approximately 0. And then the last one, make a decision. I guess we're not last one, we've got a couple more yet. So we have to compare the p-value, which is 0, is less than the alpha level, which is 0.05. We reject the null hypothesis. Okay, and then our last one is, what is our summary statement? We do have convincing evidence. We do have convincing evidence that helium balloons deflate faster than air balloons. Cool. All right, pretty straightforward, right? Interpret the p-value you got in part A in the context of this study. So remember, the idea of interpreting a p-value is saying, if I were to repeat this process many, many, many times, right, the probability of me getting at that same spot, 39.46, or more extreme or higher by pure chance alone is essentially 0. Okay, so that is essentially what we're writing in here. So we're saying, assuming that the null hypothesis is true. So assuming that the mean decrease in circumference is the same for all helium balloons and all air balloons, there is approximately 0% probability of getting a sample mean difference greater than or equal to how much by chance? How do I find the difference? Well, it's going to be up here, and when I subtracted out the two means, so I'm going to actually have to do 26.5 minus 2.1 equals 24.4. Okay, and that's it. That's all there is to sample. Next thing we're going to practice is how to know whether it's a matched pair or a two sample. That'll be fun. That's next time.